Hello friends. Today we are going to learn about differences between 4G and G5. So let's start. What are the differences between 4G and G5? Yash Infotech team believe you might be referring to 4G and 5G, which are generations of wireless technology used for mobile communications. Here are the key differences between 4G and 5G. Speed. 4G, fourth generation, 4G, networks offer faster data speeds compared to their predecessors, reaching up to hundreds of megabits per second (Mbps) under optimal conditions. 5G, fifth generation, 5G, networks provide significantly faster speeds, potentially reaching gigabit-level data rates, which are several times faster than 4G. Latency. 4G networks have relatively lower latency compared to earlier generations, with latency often measured in the range of 30 to 50 milliseconds, ms. 5G networks aim to provide ultra-low latency, with targets as low as 1 millisecond or even lower. This reduction in latency is crucial for real-time applications like augmented reality (AR), virtual reality (VR), and autonomous vehicles. Capacity and connection density. 4G networks offer improved capacity compared to 3G, enabling more simultaneous connections and better handling of high data demand. 5G networks are designed to handle a significantly higher number of connected devices per unit area, making them more suitable for the growing Internet of Things (IoT) ecosystem. Network architecture. 4G networks primarily use a traditional cellular network architecture. 5G introduces a more flexible network architecture with concepts like network slicing, which allows different virtual networks to run on the same physical infrastructure, optimized for specific use cases. Frequency bands. 4G networks predominantly operate in lower frequency bands, such as those below 6 GHz. 5G networks utilize a wider range of frequency bands, including both lower frequency bands, sub-6 GHz, for broad coverage and higher frequency bands, millimeter wave, for high-speed and dense urban deployments. Use cases. 4G networks were primarily designed to provide faster mobile internet connectivity, support multimedia applications, and improve data communication. 5G networks are intended to serve a broader range of use cases, including enhanced mobile broadband, massive IoT, critical communication services, industrial automation, smart cities, and more. Technologies. 4G networks use technologies like long-term evolution, LTE, to achieve higher data rates and improved network efficiency. 5G networks utilize new technologies like millimeter wave communication, massive multiple input multiple output, MIMO, beamforming, and advanced modulation schemes to achieve their performance goals. Energy efficiency. 4G networks introduced improvements in energy efficiency compared to earlier generations. 5G aims to further improve energy efficiency, optimizing power consumption to support both battery-operated devices and large-scale network deployments. Network slicing. 4G networks do not support the concept of network slicing, which allows a single physical network to be partitioned into multiple virtual networks tailored to different use cases. 5G network slicing is a fundamental feature of 5G, enabling the network to be divided into slices optimized for various applications, industries, or services. Each slice can have its own characteristics, including speed, latency, and capacity. Diversity of devices. While 4G supported a variety of devices including smartphones, tablets, and mobile hotspots, it wasn't designed to handle the immense diversity of devices anticipated in the IoT era. 5G is specifically designed to accommodate the diverse range of devices in the IoT ecosystem, from sensors and wearables to industrial machinery and vehicles. Edge computing. 4G. While edge computing was possible with 4G, 5G's low latency and high bandwidth capabilities make it more feasible and efficient for processing data closer to the source, reducing latency and network congestion. 5G networks enable more effective edge computing, which is crucial for applications like real-time analytics, smart cities, and autonomous vehicles. Reliability and mission-critical applications. 4G networks offered improved reliability compared to previous generations but might not have been suitable for ultra-reliable and mission-critical applications. 5G includes features to support mission-critical applications, such as those used in industries like healthcare, public safety, and industrial automation, requiring high reliability and low latency. Security enhancements. 4G networks included security measures to protect user data and communication, but new security challenges have emerged with the expansion of connectivity and IoT. 5G networks incorporate enhanced security mechanisms to address emerging threats and vulnerabilities associated with the broader range of connected devices and applications. Global standardization. 4G technologies were standardized by organizations like the Third Generation Partnership Project, 3GPP, and adopted worldwide. 5G, like 4G, 5G is standardized by 3GPP, ensuring a global framework for implementation and interoperability across different networks and regions. Transition and coexistence. 4G. Existing 4G networks coexist with newer 5G networks, allowing for a gradual transition and ensuring backward compatibility for devices. 5G networks are designed to work alongside existing 4G networks during the transition period, enabling devices to switch between networks based on availability and performance. In summary, 5G represents a leap forward in terms of capabilities, aiming to address the demands of a highly connected and data-intensive world. Its enhancements in speed, latency, capacity, and flexibility are designed to unlock new possibilities in various industries and enable innovations that were not feasible with previous generations of wireless technology. If you have any question and any doubt, so write the comment. Thank you for watching. Please like this video and subscribe our YouTube channel.